Hello and welcome to this webinar. My name is Antoine Varagna. In this webinar, we will look at InGaAs sensors used for SWIR shortwave infrared spectroscopy, specifically in the 1 to 1.7 micron region. And we'll be looking at the different approaches for cooling this type of sensors to get the best performances. The agenda is as follows. We will first look at the concept of sensitivity and signal-to-noise ratio when it comes to spectroscopy, specifically for this 1 to 1.7 micron region. We look at the implication of cooling InGaAs detectors, specifically on the sensitivity and the dynamic range, and then we'll finish with some application examples and comparing liquid nitrogen cooling versus thermoelectric cooling technology for InGaAs. So first of all, making sense of detector sensitivity. So why is it important to have good sensitivity when it comes to a detector for spectroscopy? First is to be able to identify very clearly a chemical information, and doing that, for example, in low photon fluxes experiment. For example, experiment where the samples emit very low number of photons, or there's a low concentration of a specific chemical compound that you want to study, or there are high photon losses in the optical setup, for example, in some microspectroscopy setups. You also want to have good sensitivity when it comes to looking at transient experiment, where you have, for example, a flow in front of the collection optics, and you need to capture chemical information to be able to identify the chemicals with a good signal-to-noise ratio in a very short window of time because of these transient phenomena and dynamics. Another reason could be, for example, to minimize the exposure time. So if you're dealing, for example, with chemical mapping, where you have to take a spectrum at a given position, for example, of a microscope stage XY, you need to minimize the exposure time per point, otherwise the experiment can be extremely lengthy. So any gain done at a particular point to get a good signal-to-noise ratio is extremely valuable time for this type of experiment. Finally, another example of why you would need a good sensitivity camera is, for example, to get a good signal-to-noise ratio very quickly to be able to minimize the exposure of a sample to the probe, for example, a laser or flash lamp or things like that. And some samples are more sensitive to light than others and can be degrading over time more quickly if exposed more thoroughly to the probe. So the quicker you can get this chemical information, the less probe you need to interact with a sample. So what drives sensitivity? For a detector like a CCD, an InGaAs, a CMOS, an EMCCD, the two key parameters are the quantum efficiency, so the probability to absorb a photon in the photoactive area of a sensor and convert it to a photoelectron that can be detected. The second aspect is the noise floor. It's basically on the image a grassy background here that hides the useful signal. So the higher this noise floor, the less chance basically to detect the very, very faint photon signals. So let's start with the quantum efficiency. So here's an example of plots of different quantum efficiencies for different type of detectors. The one on the right hand side, the BRDD or back illuminated deep depletion, is a CCD. And CCDs have very good quantum efficiency in the visible, but not so much when it comes to infrared. So you can see silicone based detectors not being able to capture photons beyond 1.1 microns. InGaAs detectors, on the other hand, a different type of material compared to CCDs, are able to have a lower band gap and are able to detect photons with the lower energies, typically from 1 micron up to 2.2 microns, depending on the type of InGaAs. In this presentation, we're specifically looking at the 1 micron to 1.7 micron region, and that will be covered by the sensor in green. So one of the aspects of quantum efficiency and its relation to cooling of a sensor is that by cooling the sensor, you slightly change the band gap of the material. So there are not a lot of information in the literature about the actual measurements of quantum efficiency degradation with cooling temperature. But this example here is taking a broadband tungsten source dispersed through a spectrograph with an InGaAs linear array sensor and taking the spectrum of this tungsten source at different sensor cooling temperature. So here we use 100 accumulations of 1 millisecond, for example, to get a good signal to noise ratio. And in that case, you can see that from going from a sensor cooling temperature of 0 degree, which is on the right hand side, to a sensor cooling temperature of minus 120 degree, so liquid nitrogen cooled, you can see a shift in the response at the higher wavelength. And the lower cooling for the sensor, the InGaAs sensor, the more this edge is shifting towards the lower wavelengths. So you can see that around 1625 nanometers, the QE has dropped nearly 95–96% between 0 degree and minus 80 degree cooling. It's a massive drop in the probability to actually capture a photon and detect this photon signal. Now looking at the other part of the equation, which is the noise floor, the main sources of noise in the detector are the shot noise, so that's dependent on the amount of photons incoming onto the sensor, and it follows Poisson's law effectively. It's the ultimate limit of sensitivity for pixelated detectors. Second type of noise is a readout noise. So the readout noise is whenever you digitize the information coming from a sensor, the photoelectron signal into a voltage, a read noise is introduced, and that's usually the camera detection limits for CCDs or EMCCDs or ICCDs. Dark noise is another source of noise, which is basically the generation of unwanted photoelectrons in the sensor thermally. You can tackle that noise by cooling the sensor, but as we'll see in the next slides, this is slightly different for InGaAs, where this noise is much harder to get rid of. And another type of noise is spurious noise. Clocking this discharge, for example, is an example where you're clocking the photoelectrons in your pixel matrix towards the readout of the sensor. You can introduce unwanted photoelectron generation, and this is called CIC, clocking induced discharge. So when you calculate a signal to noise ratio, you have these typical equations of your signal over your noise floor. And the noise floor is composed of the shot noise, SN, dark noise, DN, CIC noise, and RN for readout noise. For InGaAs technology, we will focus specifically on this dark noise. And the dark noise has two sources when you're getting into the infrared region of the spectrum. The first one is the actual sensor dark noise, which is common to CCDs and InGaAs as well. The second one is linked to the temperature of the scene, the black body emission from the surrounding of the sensor. So let's look at, for example, first of all, the first component of a dark noise, which is the dark current. So if you're taking again the technologies we talked about earlier on, the back-limited deep depletion CCDs, if you're cooling these sensors to the lowest cooling temperature, so typically minus 100, 120 degrees, you will get 10 to the minus 2, 10 to the minus 3 electrons per pixel per second dark current. When you move to InGaAs technology with a cutoff at 1.7 micron, you get many order of magnitude more dark current generated, typically between 10 to the power 4 and 10 to the power 5 electrons per pixel per second. So tens of kilo electrons per pixel per second. When it comes to the 2.2 micron version of these InGaAs sensors, you're talking about mega electrons per pixel per second and above. So a very high rate of generation of dark charges in the sensor, at the sensor. So when it comes to black body radiation, which is the other part of this dark noise, here is a typical example of a thermoelectrically cooled detector, like the Andor IDUS InGaAs. So a little diagram shows the sensor and all the components surrounding the sensor. So the sensor is sitting in a vacuum enclosure in a housing, and the housing is at a certain temperature. The entrance window of this camera is as well close to room temperature, so 20-25 degrees in typical laboratory environments. And then the sensor is also facing, in spectroscopy, optics within the spectrograph, so the focusing mirror and anything on the optical path. All of these components are sources of blackbody radiation, and all of these have been considered whenever you're talking about the dark noise of the acquisition. So if you're looking at the blackbody emission profile at room temperature, you can see that this is a very broad emission. It peaks at that room temperature, 20-25 degrees, it peaks around 13 microns. So the peak is actually well away from the response of a detector. But if you zoom a little bit on the region that overlaps with a sensor quantum efficiency, you have some irradiance photons that are still being emitted by black body at this room temperature, and that will be detected by the sensor. So practically what happens? So when you're measuring dark currents with sensor cooling temperature, you're kind of expecting to see the red line, the red dotted line here, the dark currents continuously dropping at a certain rate with cooling temperature. This is very much the case for the likes of CCDs that are UV visible, near-infrared sensitive. When it comes to InGaAs, you can see that depending on what you call the scene, so effectively the temperature of the experiment or the room in front of the camera, and the temperature of the coolant that you can circulate for a TE-cooled camera, the coolant that you can circulate in the camera to extract the heat. If, for example, the two of them are 30 degrees or 20 degrees or 10 degrees, you have different measurements of the dark current. And effectively, the plateau effect at the lower cooling temperature is because of the temperature of the scene, of the black body radiation. In the background, as you cool your sensor, the dark current of the sensor drops, but it's dwarfed compared to the black body emission of the experiment. So by cooling the sensor, you do impact your quantum efficiency, and you have a plateau of the dark noise performance as you cool down. So by using the equations we've looked at earlier on signal to noise ratio, and selecting photons at 1.3 micron, so not in a region where the QE is actually shifted, but where in a region where the QE is actually pretty stable with temperature. And taking a scenario, quite a low photon flux scenario of say 100 photons per pixel per second, we've plotted here different signal to noise ratio versus exposure time, and at different cooling temperatures of the sensors. As can be seen, when you're reaching minus 70 degrees, minus 80 degrees, you very much have an overlap between the different signal to noise ratio curves. There's extremely little gain between minus 70 degree cooling and minus 120 degree cooling in this particular scenario of 100 photons per pixel per second. If you actually go to even more challenging scenarios like tens of photons per pixel per second or 1 photon per pixel per second, the difference is very much the same. So that graph basically tells if you're going to cool beyond minus 70 degrees with this type of InGaAs detector in a 1 to 1.6 micron region, your signal to noise ratio will actually not improve very much. You could very much set on a detector cool at minus 70 degree, and we'll see the benefit of that in the next few slides. An example of now the impact of signal to noise ratio and cooling whenever you are in the 1.6, 1.7 micron region. So in this experiment, we're looking at the transmittance of pentane in solution and looking specifically at the first overtone of a CS stretch, which is about 3000 centimeter minus 1, and looking at again at the different cooling temperatures of the sensor. Actually, the best performance or the best absorption profile is obtained at a very moderate cooling temperature of a sensor, because the quantum efficiency curve has not been shifted. As you cool the sensor, you can see that the intensity of the magnitude of this drop of this absorption dip is reducing to a point where it's not visible when you're reaching minus 85 degrees in that case. So very much showing that cooling to very deep temperatures might have a negative effect on signal to noise in part of the SWIR spectrum. So making sense of detector dynamic range now. So dynamic range defines the ability of a detector to detect very faint signals and very bright signals in the same exposure of the sensor and without saturation of a sensor. So saturation is a phenomena where you have reached the maximum capacity of a pixel to hold the photoelectrons generated by incoming photons. And when this well depth is filled, you're getting saturation. You're not getting linear response of a sensor. You're not getting quantifiable information. On the other side of the well depth is the lowest detectable signal you can get, and that's defined by the noise floor. So typically the accessible dynamic range of a sensor and an InGaAs sensor or InGaAs camera is defined by this equation, taking into account the read noise floor just with the read noise and the dark signal. So if you were to plot this dynamic range over exposure times, here I've split the different reading mode of an InGaAs sensor. So typically you have two readout mode. One is called high capacity mode, where you have a very high well depth, but you have quite a high read noise floor, and a high sensitivity mode where the read noise is much smaller, but the well depth is also much smaller. And for each of these modes are plotted different curve at the different cooling temperatures. And specifically looking at the minus 120 degree C, the blue one, which is liquid nitrogen, and the minus 90 degree, which is typically the maximum achievable for thermoelectrically cooled InGaAs cameras, you can see some differences at the very long exposure times. If you're taking the high capacity mode, the real difference starts to appear when you're reaching 10,000 seconds. So when you're reaching 10-20 minutes exposure time. So you're talking about extremely long exposure times and quite corner cases. So in that particular case, going to very deep cooling has an advantage at the very large exposure times. So now some practical example of SWIR spectroscopy in this 1 to 1.6, 1.7 micron region using a thermoelectrically cooled InGaAs detector. So the first example here is in life science, and it's using a spectroscopy technique called diffuse reflectance spectroscopy and fluorescence. So setup is shown on the right hand side here with two spectrometers, two Shamrock 163 spectrometers from Andor, and two cameras. One is for a CCD, which will look at the fluorescence in the visible. It's a back emitted deep depletion camera. And the second one is an IDUS InGaAs camera to look at the shortwave infrared response. And the graphs C and D, for example, show the InGaAs capture of the diffuse reflectance signal with the InGaAs camera. On the left-hand side is an idea of a stained tissue sample image used for histopathology, and looking at the the visible image, if you want, of a structure of the lung sample, and then the group does spectroscopy with fiber optic probe, collect the diffuse reflectance spectrum, and the spectrum are plotted on C and D, and you can see very subtle reflectance differences between healthy tissues, so normal lungs at the top, and tissues with tumors at the bottom here. Very, very subtle differences, especially around the 700 nanometer, and the peaks as well in the 1 to 1.1 micron region. Another example is in chemistry. So here we're looking at monitoring the catalysis kinetics of a particular catalysis between the two species that are shown on the graph on the left-hand side here, and introduction of H2O2 as a catalyst. So over a number of seconds here, we're looking at the spectrum, the Raman spectrum, with a 1064 nanometer laser. And we're looking specifically at the carbon-carbon bond around 1600, 1700 centimeter minus 1, and looking at over time the evolution of the intensity of that line, and ratioing that to the aromatic breathing mode, the big large peak in the middle here, which will be undisrupted during the catalysis reaction. And you basically look at the ratio of intensity of the two bands as catalysis takes place, and plotting the graph on the left hand side, looking at the this conversion over time and being able to measure the conversion speed. Again, this was done by Professor Wesley Brown at University of Groningen using an hydrogen gas and a little Shamrock 163 spectrometer. Another example in chemistry, again with the same group, is looking at singlet oxygens. So singlet oxygens are an important bit of information for a certain chemical reactions. And here, using a 532 nanometer laser with 300 milliwatts and decreasing the exposure time of the InGaAs sensor, we're looking at the emission peak at 1275 nanometer with these decreased exposure times using the Andor alias InGaAs camera and the Shamrock 163 spectrometer. Another example would be in material science. So here looking at the fluorescence properties of what you call functional carbon nanotubes. So in that particular case, we're looking at DNA wrapped single wall carbon nanotubes, and the spectrum changes when adding different type of compounds. So the compound the added compound within the carbon nanotube is probed with a 560 nanometer laser, and we're looking at the differences of spectrum on the left-hand side between the kind of base carbon nanotubes and when the different compounds have been added. And these are a type of research for the likes of biosensors, so being able to inject luminescent material within carbon nanotubes, within tissues or within organisms, and being able to do some level of imaging, for example, fluorescence imaging. So these are novel ways to deliver these fluorescent probes to different parts of different tissues or different parts of the body. Another example in material science is the likes of 2D semiconductors. So for example, here we're looking at transition metal dechalcogenates, and these are semiconductors with very distinct photoluminescence properties. So the little insert here shows some of the crystalline structure, And we're looking really at the 2D, what you call low dimension 2D materials here, and looking at unique emission properties. So here, the group at University of Dortmund used again another InGaAs with a camera 193 spectrograph, and looking at the fluorescent peak around 1.07, 1.08 electron volts in the setup, the microspectroscopy setup. So a summary of this discussion here. So should you consider deep cooling for swirl spectroscopy in this 1 to 1.7 micron bracket? So with liquid nitrogen, you have a fixed cooling temperature effectively to minus 120 degrees. Sometimes the dewar containing the liquid nitrogen is heated to maybe tweak a little bit the temperature, but these are typically really set at minus 120 degrees. With thermoelectric cooling, temperature can be adjusted from room temperature down to, all the way down to minus 90 degrees C, specifically for InGaAs detectors. So based on the observation we had earlier on, deep cooling in InGaAs below minus 70 degree doesn't really improve the sensitivity, the signal to noise ratio in the 1 to 1.6 micron region. However, when you're looking at the 1.6 to 1.7 micron region, we have seen that the signal to noise ratio can dramatically degrade because of the shift of the response in quantum efficiency towards the higher energies. We also seen that deep cooling InGaAs sensors down below minus 90 degree does actually provide some benefits for dynamic range. However, this is only the case whenever you're dealing with exposure times in the tens of minutes. So, liquid nitrogen cooled InGaAs or TIN cooled InGaAs. So, as we've said, the advantage of a liquid nitrogen is really around the dynamic range, especially if you are dealing with exposure times of 15 to 20 minutes, which is quite a corner case, but nevertheless, some experiments need that type of exposure time. However, we've seen as well that by doing so, we're worsening the sensitivity in the region 1.6 to 1.7 micron. So liquid nitrogen would not be recommended for that region of the spectrum. On the other hand, we've seen that T cooling to minus 70 or minus 90 degree actually does a very good job for the vast majority of spectroscopy experiment in that region when it comes to photoluminescence, Raman absorption, singlet oxygen, and so on and so on. Even at the low photon fluxes, you're dealing with experiments that are using very weak emitters. T cooling cameras don't need any type of addition of liquid nitrogen. There's no hazardous handling of liquid nitrogen in a lab for this type of detectors. T cooling is maintenance free. These are cameras, the sensors are packaged in a vacuum environments, are guaranteed for many years, protect the sensors for any degradations of performance, and are low running costs because, as trivial as it can sound, a liquid nitrogen cooled camera will consume a certain amount of liquid nitrogen over time, a certain amount of efforts to maintain, and all of these are costs to consider over time, over a number of years. And finally, considering the portability. So T-cooled InGaAs cameras are very compact. They can be moved very easily from one lab to the other, be used for in-field applications as well, for example, and minimize the space taken on an experimental table or optical table, for example. This is the end of this webinar. Thank you very much for your attention.